So far, we've gone through a lot of conceptual description of the LC oscillator circuit, and we've derived a lot of equations in principle, but we haven't done any particular numerical example problems. So here's one. The LC oscillator circuit is made of a 6-volt battery, a 15 picofarad capacitor, and an unknown value of inductance. However, we're told that the frequency at which this circuit oscillates is 919 kilohertz. Now you may have noticed before that the AM band of your radio is expressed in kilohertz, where the FM band of your radio is expressed in megahertz. So if you want, you can think of this as a radio frequency somewhere just a little below 1,000 kilohertz, 919 kilohertz. So if that's the value of the frequency, then what's the value of omega, the angular frequency? As you know, angular frequency is expressed in radians per second, and standard frequency is measured in cycles per second. Well, if we relate this to the behavior of motion in a circle, a full cycle is all the way around. In other words, 2 pi radians is equivalent to 1 cycle. So in that regard, angular frequency is always 2 pi multiplied by standard frequency. So the answer to question number 1, if the standard frequency is 919 kilohertz, then the angular frequency is 2 pi times 919. In other words, 2 pi rad per cycle multiplied by 919, 1,000 by the way, 919 times 10 to the third cycle per second. Cycles cancel out. We'll be left with radians per second. And if you grab a calculator, multiply 2 pi times 919, you get an angular frequency of 5.774 times 10 to the 6th radians per second. Or if you want 5.774, we can just say mega rads per second. All right. What's the value of the unknown inductance? When a mass vibrates on a spring, pull it back, establish some amplitude to the vibration. I know that the angular frequency for a mechanical oscillator is the square root of k over m. Does that help me remember the expression for the angular frequency of an electrical oscillator? The analogous quantity for spring stiffness is the inverse of capacitance. The analogous quantity for mass is inductance. Oh yeah, that's right. The angular frequency of an electrical oscillator is the square root of 1 over LC. So if we square both sides of that equation, omega squared is 1 over LC, and then with a little cross multiplying, inductance is equal to 1 over omega squared times capacitance. So given our example values, this would be 1 over the square root of 5.774 times 10 to the 6th quantity squared, and 15 times 10 to the negative 12th, 15 picofarads. Yeah, that was our given value. So crunch that out on your calculator. And you should get very nearly the inductance is equal to 2 times 10 to the negative third. Oh, I've left out the units. Now I leave it up to you as an exercise to convince yourself that this is 2 times 10 to the negative third henries, or 0.002 Henry if you prefer. So far so good. What's the maximum charge on the capacitor, and what's the maximum amount of potential energy stored in the capacitor? Well, this should be easy. maximum amount of charge is just capacitance times EMF. So this is 15 picofarads times 6 volts, which gives us 90 picocoulombs. Now if you want to get the energy, you've got three options. 1/2 maximum charge times battery voltage, maximum charge squared divided by 2 times capacitance, or 1/2 capacitance times voltage squared. Well, if you do any one of these calculations, you'll get the same answer, and that answer comes out to 270 picojoules. What's the maximum amount of current flowing in this circuit? When the switch is moved to position B, initially the upper plate is positive, the bottom plate is negative, electric field lines exist between the plates, but there's no magnetic field at all. In time, some of those electric field lines disappear as the charge goes from its maximum value down to some lesser value. This is due to the current that's conducting electricity off of the capacitor. It's not at its maximum value yet, so there's just a little bit of magnetic field. But give it some more time, and this charge goes all the way to 0. At that point, the current is its maximum value, and the maximum magnetic field exists in the inductor. There's no longer any energy in the capacitor. All of the energy is now in the inductor. So let's see if we can figure out what the maximum amount of current is. Well, there's a few ways to go about this. How about we express the equation for the way charge is varying in time on the capacitor? Well, that's equal to CE cosine omega t. So current should be the derivative. So it should be equal to negative omega CE sine omega t. Now if we want the maximum value, then that should just be equal to omega times c times epsilon. So we found our value for omega earlier. It's 5.774 times 10 to the 6th. 5.774 times 10 to the 6th. That's radians per second. The capacitance is 15 times 10 to the negative 12th. That's farads. And the EMF is 6. That's volts. So 5.774 times 10 to the 6th multiplied by 15 times 10 to the negative 12th multiplied by 6 gives us a fairly small value. Our maximum current is equal to just a little more than half of a milliamp. We get 5.2 times 10 to the negative 4th amps. Good enough. What's the maximum amount of energy in the inductor? Energy in an inductor is 1/2 L I squared. Well, at any instant, 1/2 L instantaneous I squared. But if we're trying to find the max value, oh yeah, then we should use the maximum amount of current, which we just found. Oh, by the way, please recognize that this equation is very much like kinetic energy is 1/2 mv squared. The analog to velocity is current, the analog to mass is inductance, and the energy in the magnetic field is kind of like the kinetic energy. Okay, so let's plug in the values we have. The maximum amount of energy in the inductor is 1/2 times, what was our inductance? Oh yeah, 2 millihenries. 2 times 10 to the negative 3rd henries times 5.2 times 10 to the negative 4th amps. That's squared. So if we square the maximum current, and multiply by the inductance, and then divide that by 2, we get, oh, surprise, surprise, we get that the maximum energy in the inductor is equal to 270 picojoules. Of course it is. Energy is a conserved quantity. The maximum energy in the capacitor occurs when the energy is all in the electric field. When that electric field totally collapses, then you have a maximum amount of magnetic field in the inductor. But the energies should equate. So the 270 picojoules of energy associated with maximum electric field matches the 270 picojoules of energy associated with the maximum magnetic field. How much current is in the circuit when the charge on the capacitor is 55 picofarads? Now keep in mind, as we found earlier, the maximum charge on the capacitor was 90 picocoulombs. Oh, did I say picofarad? Shame on me. Picocoulombs. Well, the maximum energy at any point should equal the sum of the energy in the inductor plus the energy in the capacitor. Maximum energy is the maximum charge on the capacitor squared divided by 2c. Energy in the inductor is 1/2 L instantaneous current squared, and energy in the capacitor is lowercase q squared over 2c. Well, if we rearrange this equation, we'll get something we've seen in one of our previous lessons. The current at any instant is equal to the square root of 1 over LC times the square root of maximum charge squared minus instantaneous charge squared. But then again, the square root of 1 over LC is just the angular frequency. So we can say the current at any instant is the angular frequency multiplied by maximum charge squared minus instantaneous charge squared. Let's go down to here where we have some room. So this is 5.774 times 10 to the 6th radians per second times the square root of 90 picocoulombs, so 90 times 10 to the negative 12th squared, minus, we're given 55 picocoulombs as a value, so minus 55 times 10 to the negative 12th squared. Sorry if my writing's getting a little messy. So let's see what this comes out to. 55 picocoulombs squared subtracted from 90 picocoulombs squared. We take the square root of that and we multiply it times 5.774 times 10 to the 6th, and we get 0.000411, or in other words 4.11 times 10 to the negative 4th amps. So you notice that's a little bit less than our maximum current of 5.2 times 10 to the negative 4th amps. So at least the answer agrees within the possible bounds for the current. Our last question, let's move this down here. Express the charge on the capacitor as some function of time. Well, as we know, in general, the charge on a capacitor should be equal to the maximum charge times cosine of omega t. So this is just going to be equal to 90 picocoulombs times cosine of 5.774 times 10 to the 6th radians per second multiplied by t. Simple enough. Don't have to do any more than that. So there's an example problem of how we might apply some numerical values to the behavior of the LC oscillating circuit.